All right, in this video, we're going to look at separable differential equations, and this is the technique you use to actually find the solution to a differential equation rather than being told the solution and verifying it through differentiation or something like that. Going to start off with some pretty simple ones. Actually, there's only three, but this one is pretty straightforward. The reason it's called separable differential equations is because part of the process involves separating variables, which means you want to get all of your y's on one side and all of your x's on the other side. And in this case, the way I'm going to do this one is I will cross multiply. dy dx equals x over y. If you cross multiply, you get dy times y, which I'm going to write in the order y dy equals dx times x, which I'm going to write as x dx. And now if you look at each side of the equation, we have almost an integral. We have the y dy. All we're missing is the antiderivative sign. But if I do the integral of the left side, I'm going to have to do the integral of the right side. And then we will integrate both sides after we separate the variables. The integral of y is y squared over 2. And technically there is a constant here, equals the antiderivative of x is x squared over 2. And there is a constant here. I'm going to call it something different because c is already taken. However, normally I don't write my plus c right here. I just don't write one at all. And I'll put a plus c on this side of the equation. And that's because they both kind of morph together. If I have a constant on this side, I could simply subtract it. And if you have some random constant minus some random constant, you're still just left with some random constant. Um, so there's going to be the solution to this differential equation. And then there's going to be some algebra tied to this. I could, if I wanted, just to clean this up a little bit more, this isn't absolutely necessary, but I could double everything in the equation. And y squared over 2 times 2 is simply y squared equals x squared over 2 times 2 is simply x squared. And 2 times c, well, remember, c is just some random constant. If you want to write 2c, it's not wrong. But 2 times some unknown arbitrary constant is still some unknown arbitrary constant. So that would count as a solution as well. Let's try a different one. Let's look at this one. It's a little bit uglier, but it's going to be pretty much along the same lines. To separate this, I have dy dx equals this. I will cross multiply again. That gives me 6y squared equals, I forgot the dy, 6y squared dy equals x squared minus 3 times the dx, and then we will integrate both sides of the equation in order to find the solution. Ooh, that's an ugly integral sign. Antiderivative of 6y squared is 6y cubed over 3, which is 2y cubed. I'm not going to write the plus c on the left side. Antiderivative of x squared is x cubed over 3 minus 3x, and here's my plus c. And we could stop right here. I'm going to go one step further and finish solving this. I'm going to divide by 2, or multiply everything by 1/2, which would give me y cubed is equal to x cubed over 6 minus 3x over 2 plus. And if you take half of c, you still have some unknown constant. And then I would take the cubed root of both sides. And here's where you have to be careful with that plus c, because the plus c will be part of the cubed root. So the plus c needs to be inside that radical, and we're left with y equals the cubed root of all of this stuff. X cubed over 6 minus 3x over 2 plus some constant, all raised to the 1/3 power. And that would be your solution. And then I could give you an initial condition and say y of 0 equals 5 or something like that. And you could use that information to solve for c. But right now I'm just trying to get that initial solution after you separate and integrate. This one's going to be a little bit tougher. It's not primed and ready to cross multiply. The first thing I'm going to do is change my y prime to dy dx. So I'll have dy dx equals all this stuff. So I have 3y and 2 plus x. And then I need to separate my variables. I want my y's on the left side and my x's on the right side. Now this one's not going to be as clean as a simple cross multiplying. I'm going to start by multiplying both sides by dx. Because if I do that, my dx's here cancel, and I'm left with 2 plus x dy equals 3y dx. And now I need to move this 2 plus x to the right side and this 3y to the left side. And I'm going to do that by dividing by 3y and 2 plus x. If you divide by both of them, it will end up sending the x's to the right side and the y's to the left side. Let's cancel. 2 plus x cancels. 3y, 3y cancels, leaving me with the antiderivative. Well, let's get the antiderivative later. 1 over 3y dy equals 1 over 2 plus x dx. And now we are ready to integrate both sides. So I'll take the antiderivative. The one on the right side is pretty simple. The one on the right side is going to be the natural log of 2 plus x, because the top is the derivative of the bottom plus some unknown constant. The left side is also going to be a natural log, but in order to make the top the derivative of the bottom, I have to multiply by 3 on top. I will offset that with the 1/3. So the left side is 1/3 natural log of 3y. Good, 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 good. And now I'm going to start playing some algebra to clean this up. Lion King in the background. Did y'all hear the music? All right. Let's see. I will multiply by 3 to get rid of that 1/3. That's going to give me the ln of 3y equals 3 ln of 2 plus x plus some constant. If you triple the constant, it's still some unknown constant. And then if I wanted to continue solving for y, I will exponentiate both sides, make both sides exponents on e. And that leaves me with e to the ln of 3y, so that's 3y equals e to the 3 ln. I'm going to play around with this. E to the 3 ln. But 3 ln is the same as ln of 2 plus x to the 3rd power plus some constant. Are we good with that? We're good with that? And I'm ignoring the absolute values for now. And I'm kind of wishing I hadn't chosen this problem yet because I'm trying to keep this video short. We will go over in class what happens to these absolute values and why I'm kind of ignoring them for now. But I just want to show you some algebra behind this. Let's see. I want to clean up the right side. There is a property of exponents that says like x to the a times x to the b is equal to x to the a plus b, right? That's kind of what I have here in the exponent on my e. I have e to the something plus something. I could rewrite that as e to the ln of 2 plus x all cubed times e to the c. And I have 3y over here. And then if you look at e to the c, if I take e and I raise it to some unknown random number, that's still going to give me some unknown random number, which I'm going to call a. So now I'm down to 3y equals e to the ln stuff times a, which I'm going to call that a, e to the ln of stuff. Good? And e to the ln of anything is just the anything, so this is 3y equals a times 2 plus x cubed. Good? And then finally, I will divide by 3. Y is equal to a times 2 plus x all cubed divided by 3. And that did a whole lot of cleaning up based on how ugly it originally started. So that one may have been a little bit more complex than I should have done here in this first introduction. You have the separable differential equations. But hopefully this is enough to get the ball rolling, and we will hammer out some of the finer details later.